Okay, how's everybody today?
Alhamdulillah, Prof. Good.
Okay, good.
Good, madam.
You know that all my classes will be recorded, right? All of you. Let me pause it. All right, let's continue. I'm recording again. Okay, let's continue. Where did we stop last time? Anybody?
Defects. We start at defects, and madam wants to continue explaining about the Auger recombination.
OJ. China
OJ.
OJ.
OJ. OJ.
Yes, OJ. The pronunciation is OJ. Even me with my lecturers friends, I will even correct my friends if they speak. You mention any English word which are not correct. I will correct my friends. I'm the kind of person who cannot hear anything wrong. So, and I will appreciate also people to tell me if I'm wrong, something like that. Okay. So, and I will share my screen now. I think we should have a quiz. Just to test your understanding, maybe next week, because in the previous semesters, my fault was I had the quiz quite late, and the student think they understand, and suddenly in the middle they just realize, wow, they failed the quiz. So then it's a bit too late. So maybe we have a quiz on Thursday next week. So it'll be everything until today. Okay, it will be everything until today. It will be a closed book, so you cannot open your notes on the internet. Can you please remind me on Tuesday next week? No, Monday. Monday remind me so that I will make the paper, the quiz paper. I'm not sure if I'm going to take leave or not on Monday. I will let you know. If I take a leave, I will give you some homework for you to do, to watch some videos. So but your task is to remind me to make the quiz question. So on Thursday I will give you the quiz, inshallah. So
It will be conducted online or face to face?
oh, good question. Anybody here in quarantine or positive? No?
Not yet, madam.
Not yet. So you're making dua that you'll be in quarantine or what? So if everything okay, we'll make it face to face. If something wrong, one person, actually if one, we can still make it face to face, right? We'll see. I will ask me on Wednesday, a day before, how we going to have a face to face class, or we going to do it online. Okay, all right. But make sure you study. So I told you, right, we're going to have only maximum of 4 quizzes. I will take the best 3 out of 4, inshallah. That's the aim. Did I tell you when I did my degree, there is no quiz. During my undergraduates, I don't know, I think there's no quizzes, there's no assignment, there's midterm, and then final. So if I think 70%, I think final. So if anybody screw the final, that's it. So that's why I like that kind of arrangement, so that I don't have to study a lot. So but in Malaysia, students like to have many quizzes, many assignments, and then you take the average, which means that in the end you don't have time to do other things. When I was studying undergraduate, I have a lot of time. I can do many things throughout the semester. At the end, I will study like crazy. then I will score. So but in Malaysia you cannot. Yeah. So that's why here I will try to only have 4 quizzes throughout the semester, take the best 3, then we'll have an assignment. That one is 30%, quite a lot. So make sure you do your assignment properly. Normally, the one that student cannot score is the quiz and final exam. Assignment, if you are really bad, I will ask you to do it again. If I'm kind enough. If I feel that I'm not kind, I will just say, okay, you just get whatever marks you deserve. Well, if I'm in a good mood, I will say, okay, I'll give you another chance to present. Okay, now let's look here. All right, so we have covered band to band for non-radiative recombination last time. We have band to band for indirect band gap material. If this happens for indirect band gap material, you have non-radiative recombination, which means that it's producing phonon, which are heat, okay, when it recombines. So another way that you can have non-radiative recombination is through defects, and we talk about this, whereby when you have defects in the structure, it will manifest itself in terms of energy level inside the band gap. So the thing about these defects, right? Defects that you see here, there are many types of defects. Sometimes, I'm telling you, not all defects will give rise to energy level inside the band gap. Not all. Sometimes the defects can look very bad in the microscope, but it doesn't translate to inside the energy band gap, which means that it's good. It means that you will still get good light out of the semiconductor. So what example of that? For example, one example of that is blue. Which semiconductor gives out blue light? Anybody? I give you 1 second to Google. Which semiconductor material gives out blue light?
Gallium nitride, madam.
Good. Gallium nitride. So gallium nitride is something that being discovered later. Previously we know silicon, germanium. That's the early semiconductor that been be able to they found it, and they able to fabricate, to make it into devices. Because although all the semiconductors are materials are similar, they're all semiconductor materials, but how to fabricate, how to make it into device, what the contacts are different. So they are not the same. That if you're going to make a device, it's not the same way for all of the semiconductor materials. So gallium nitride have its own challenges, that for many years they couldn't make device out of gallium nitride, although they know the band gap and so on. So at the end, with technology, with advancement of technology, they're able to make diodes out of gallium nitride. And when they look in the microscope, they were shocked to see there's a lot of defects, really bad defects. But they thought that it will not give out light because of the too many defects, and the defects look horrible. But fortunately, when they do when they forward bias the diode, then they can see blue light coming out. So somehow this defect is not affecting the band gap. So there are things like that as well. So then previously, the technology, right? We have CD, CD player, CD. Then after that you have DVD, right? So have you seen the DVD player? It says Blu-ray.
Blu-ray card.
Huh?
Blu-ray.
Blu-ray. So previously there's no Blu-ray. The Blu-ray technology comes after we are able to make up laser out of gallium nitride. So they use gallium nitride to make blue laser to read the DVD, so they can read it faster. So that's why DVD, you can put more information in DVD compared to CD, because you have something to read it, the gallium nitride, and it calls Blu-ray. Why is it Blu-ray? Because they are using gallium nitride material as a laser to read the DVD. So that's how it works. So all colors so have its own applications. Okay. Right, so we talk about defects. So not all defects will give rise to, the trap inside the band gap. And finally, you have OJ recombination. OJ recombination is nothing, is only happens, okay, this is a slightly special. Normally in exam, I will not cover this. But you can, maybe, I don't know. But if you're in the semiconductor field, you should know all three. The common ones are this one. If you take non-radiative recombination, the first culprit is you think the defects. Because of course you will not be stupid enough to use a direct band-to-band direct in order to get non-radiative recombination. So you know this is a indirect band gap material, you will not get light out. Okay, so this is, but I'm really sorry, students still make some stupid decision in the final exam, because in the final exam you have design question whereby I will give you criteria. I want a device that can do this. So you are supposed to choose the material, you're supposed to tell me the structure, you're supposed to tell me how does it work, why do you choose this material, why you choose why that kind of structure. But students still answer for something that needs light coming out. They still choose indirect band gap material, and it's open book, So can you imagine why most of them fail? Because they're not thinking. So I hope none of you will do the mistake. Okay, so right, so then so you have defects. Now OJ recombination is just like it's slightly a bit weird. So OJ recombination only occurs at very high very high injection current. For example, for LED or laser, sometimes it can happen when you have too many free carriers. OJ recombination can occur. So OJ recombination doesn't occur for low free carriers, low concentration of free carriers, or low injection current. What is injection current? Injection current is just the current that you put into LED or laser to make it to give out light. After this, we'll learn about PN junction, how to make LED and laser works. So now, okay, so this normal, our normal. So whenever you draw energy band diagram, make sure you label everything. If there's a lot of marks, I will deduct marks for the things that you don't label. So be as detailed as possible. Sometimes students don't label the band gap. So sometimes I put in the writing the band gap is 1.4 eV, for example. So what you're supposed to do, you're supposed to draw here 1.4 eV, the band gap, right? And then I have another material, I say maybe the band gap is 0.7 eV. Then you level 0.7 eV. And then when you draw, make sure the arrow is touching the other the two band gap. Okay, and I label this. Okay, right. So now OJ recombination. So whenever you have normally, right, you say what, okay, let me ask again, what is recombination, Badul Amin?
Apa dia tadi tu?
Recombination, what is recombination?
Recombination yang dia terbalik tu kan madam?
Terbalik apa?
Yang apa yang dekat gambar tu yang dia dari EV.
I don't know, you tell me.
Oh.
I speak English. Because no point of me teaching all this and you don't know what recombination is. No point. Yes.
I think I don't remember, madam.
Oh, how you going to understand semua ni? Awak tak ingat benda-benda basic ni, Amin. Sekarang saya dah warning, mungkin awak akan fail quiz and courses ni nanti. Awal-awal ni kena ingat semua benda. Call somebody to explain recombination. Choose one person. Quickly. Amin.
Haziq, can you help me?
Haziq, what is the combination?
Recombination is a process of electron losing free carrier, electron release energy from conduction bands to valence band, and from holes to valence band to conduction band. If it's hole, from valence band to conduction band.
Okay, good. So sure all of you know, that is basic. If you don't know, as I said, you need to study. You need to study. Make sure after the class you don't forget everything that I'm teaching you. Otherwise, you'll be in deep trouble. So okay. So electron will recombine from conduction band to valence band like this. Okay. So in a normal process where not many of the free carriers here, you know, if it's a direct band gap material, it will release photon. However, if there are a lot of free carriers here, what happens is when electron goes from conduction band to valence band, recombine from valence band to a conduction band to valence band, it will release energy. So, but for OGA recombination, instead of the energy being released as photon or phonon, this energy released are being taken by another electron over here in the conduction band to go to a higher level. So it looks like that. So the energy is being transferred. So as we know, energy cannot be lost. So the energy being transferred. So instead of it gives out as a photon or phonon, when you have a lot of free carriers, the energy be absorbed by one of the free carriers to go to a higher energy level. Okay, so if it's a hole, if I draw a hole will go from here. You have a lot of holes here. When the hole recombines, it will go there, right? So for OJ4 holes, instead of releasing photon or phonon, it will promote another hole to go to a more of energy. So for electron, higher energy going up, for hole, higher energy going down. So that's OJ. So which means that is it good or bad? It's not good for us LED and laser designer, because we want any recombination to give out light. But instead, when we put a lot of current in, we put a lot of energy current. You put the current in, which is also you don't want your battery. The higher the battery, you want it all to give out to bright light. But instead of getting a bright light, you are just you don't get a bright light. Why? You're just promoting this whole electron to go to a higher energy, hole to higher energy. So when it goes to higher energy, what happens is after sometimes it will fall down here. Then nothing happens. Which means it's not efficient for the LED or laser to have OJ recombination. And that's why OJ recombination is a non-radiative recombination, because it doesn't give out light. Okay, any question?
Madam, can I ask something?
Sure.
So when this OJ recombination occur, man? I mean,
When?
is it a process that we make it naturally happen?
No, it happens when there's a lot of free carriers here. Kata dia punya condition tu, you need to have a lot of free carriers. How do you get a lot of free carriers? Is when you inject a lot of current. For example, you letak voltage yang tinggi. If you increase the voltage, it means you increase the current. Therefore, you have more free carriers. Therefore, probability for OJ become higher. Okay. Any more question? No? Okay, good. So what else should we are supposed to discuss? Anything else? I think there's other things, right? Lattice. Oh, we need to talk about. We need to talk about defects now. Now we talk about that. Let's go back to lattice. Let's go back to lattice and lattice constant here. Okay. So A here is the lattice constant. It's the distance between atom to atom in a semiconductor. So it can be different. It will be a different value for different what do you call it? Different semiconductor material. Okay. Now I want to talk about homojunction and heterojunction. Okay, you know, in the starting of these few weeks, I introduced a lot of terminology. So you need to understand the whole, everything, all of the terminology that I teach you. Then this terminology will be used later in our course. This is just introduction, brothers and sisters. We are not entering the semiconductor device yet. This is just semiconductor physics. We haven't entered semiconductor device. If I don't do this, you will not understand semiconductor device. Then it's just a waste of time teaching if you don't understand. So so all these are very important. If you don't know, if you don't remember these basics, you'll be in trouble later on because you couldn't understand semiconductor device. If all this you don't master yet. Okay, I'm warning you many times. If you don't take my warnings, it's up to you if you fail. It's no longer my fault. Okay, now, okay, let's look at this. Okay, I want to copy this lattice. Okay, this is a lattice. So if it's a good ideal lattice, you become like this. And then you have the point defect over there. You have the lattice constant over there. Now, and then I want to introduce homojunction. Let's not talk about junction, structure lah, structure. Junction to PN junction untuk belajar kan. Homostructure and heterostructure. Okay, homostructure means all the structure inside the material are coming from one type of semiconductor material. So for example, if I want to make kuih lapis, let's go for kuih lapis again. Anybody tried kuih lapis since our last class? If you're not, I highly encourage you to go and find kuih lapis in the shop. Okay, then you understand because this kuih lapis will come again and again in our class. Because that's the easiest way for me to explain. Because these things are you cannot see. So this is my kuih lapis. Okay, my kuih lapis. So the way I make my kuih lapis, I can make it all with the same material, all tepung beras, all rice flour. So I make all here. Okay, with one type of material. I can make many layers, but many layers of the same material. And this is called homostructure. And this is called homostructure. Homo means one. So all with one type of semiconductor material. Okay, that's one. Let's talk about, how about heterostructure? So if it's a heterostructure, I still have layers of the epitaxial layers. I can make layer by layer by layer by layer, but I can mix the material. For example, if you go to the advanced shop, not the kampung one, you can have kuih lapis with, you know, kacang with nuts. So one layer of rice flour, you have nuts and you have like durian or things like that, right? So you can have with different material. So let's say so I can have a layer of this. And then I put another layer of another material. And then I can make the same material or not. So this is called heterostructure. More than one semiconductor material in one structure is called heterostructure. Okay, so I can make it like this. I can make it green, orange, green, or I can make orange, green, whatever it is. As long as it's more than one type of material, it becomes heterostructure. Any question? Next question. Okay, you don't have question. You always don't have question for me. Then if I ask you, you cannot answer. But you don't ask me question, I also don't understand. So my question is, okay, since I give you another chance, ask me question. After that, I will ask you question.
Okay, madam.
Yes?
If there only two
Ada.
type of material that need to combine so that it can call heterostructure, or we can have more than two type of material.
Adwa, I already said more than two, more than one. More than one, it means 1,000 is heterostructure. Okay, so meaning more than one, 1,000, 1,000,000 is more than one, right? 5 is more than one, right? So yes, anything more than one is heterostructure. Any more question?
I have a
Yes.
question.
Okay.
This will the combination of the material change the lattice structure?
Okay, good question. This is where we're going next. Okay, so now, so if it's all you know, with the same material, it's okay, everything good, right? Kuih lapis, you make it all from different same material, no problem, it comes very nice. But if you try to change, you put nuts in, right? One layer rice flour, next layer nuts. Do you think you will get a good layer on top? No. Will it stick to each other?
Yes.
Huh? You put a layer, so you cook already one layer with rice flour and you put nuts in. The next one, you put nuts on top of the cooked layer.
No, it will not fit perfectly.
It will not fit perfectly. It won't stick like how if it's the same material. If you don't trust me, go to your mother's kitchen. After this, you try. Okay, or you can do experiment in your own mahalla. Okay, so you will not be able to stick as much as how good as it is if you use the same material. Okay, the same as semiconductor material. So what happened is, so let's this, okay, what happened is, so I need to okay. So this my so let's say this is my first layer. So let's call this silicon. My lattice, my silicon lattice. Okay, I give you 1 second. Can anybody 2 seconds? Search what is the lattice constant for silicon. This is a practice for you for your exam. In the exam, you have to, you know, You have to be able to search. So what is the lattice constant for silicon?
Uh, 5.4310.
5.431 ampere.
Ampere?
Sorry, 5.431.
This is
A
called, this is called Armstrong.
Armstrong.
Armstrong is a unit. What is Armstrong? One Armstrong is 1 times 10 to minus 10 meter. Okay, so normally we just say 5.43 Armstrong. If you know, you should know what Armstrong means. It's just you have nano, you have pico, but Armstrong is with the meter. 1 times 10 minus 10 meter. Okay, so it's because it's a unit used mostly to explain this. So 5.43 means that this distance here is 5.43 Armstrong. Okay, let's say I use another material, okay, with the purple apa ni, atoms over here, with let's put hypothetical another name B, material B. Material B, I have I'm using a material which is slightly different, slightly bigger lattice constant. So maybe this is 5.56 Armstrong. Okay, B. So if the lattice constant is not very far, you can still the atoms can still bond. So for example here in this silicon structure, the whole atoms are bonded together, covalently bond. So here in the material B, all the material here is also covalently bond. But now how about here when interface between the two materials? So if that's the case, if the lattice constant is not very much difference, you can still bond, but with some stress or strain. Okay, I want you to go and learn on your own. What is stress? What is strain? I will not teach you. Not everything I will spoon feed, but go and read what is stress and strain in semiconductor. So what happens is, I'll draw this blue line. So it will try to bond. So it will try bond here. This is bond here, bond here, bond here. This not. You can see. This my drawing is not good. Okay, this is not resembling what I want. I need to make it bigger in order for you to see it. So I need to just draw it again, make it bigger. I need to make it bigger. Maybe double. Maybe double. Maybe this, it will see it better. So this will bond to that. This will bond to this. This will bond to that. This will bond to this. This will bond like that. So all these blue line are the bond. So you can see here. If you can see here, at the interface here, there's stress or strain. One of it is stretching, another one is to make it small. So this is stretching it. Sometimes you can have it smaller half, and then you make it small like this. So this stress or strain, when you put two materials together, it will try to bond, but it introduces stress or strain inside the structure. So if the stress or strain beyond a certain limit, and the limit is different from one material to another, what happens is, okay, I will show you, okay, so if I keep on drawing this, then you will see. So see, if I keep on drawing this, and I have to this. You can see the bond here now become too much. Too much. And this will go further and further. So at one point, it cannot go further anymore, it breaks. The bond breaks. Okay, when the bond breaks, okay, so when the bond breaks, it will break at certain, so there will be some atom that will not be bonded. And then in the others, it will start to bond again. Whenever there's a break of the bond, this causes defect. Okay, this causes defects. So can you imagine these are similar number, so similar lattice constant. If the lattice constant is too big, when you put the two material, sometimes you try to bond but with a lot of defects. So that's why when we make heterostructure, we need to be careful of what kind of material we choose. But the question, okay, ask me question before I ask you question. I have a question I want you to ask me, but if you don't ask me, I will ask you. Okay, give you 1 minute, no, 30 seconds to ask me.
What happened to the band gap level?
Band gap will still be the same. So for example here, that's a good question as well, but another question that I want to ask you. Since you asked, it's good, I will explain. So how about the band gap? Okay, that's a good question. I give you like 3 minutes to answer that question. I give you, for example, let's draw this heterostructure here. The yellow one has a band gap of 1.6 EV, and this is 1 EV, so 1.6 EV. Can you draw the band gap? And this is all intrinsic semiconductor. 2 minutes lah. It shouldn't take you too long to draw. And everybody have to show their drawing after this. Thanks to that the brother who asked the question. I can see who asked the question just now. Good question, though. If you finish, let me know, everybody. Shouldn't take you long. Okay, finish. Time's up. Show me your drawing. How to show me your drawing? How to show me? Just put it on the. You can put to your video camera. Who wants to start first? Mukmino, let's see yours. You need to bring it close to the, I think, close to the camera, no? Lagi closer, it doesn't focus. Okay, if you're not focusing, everybody paste your answer in the Telegram group. All of you take a photo, put in the Telegram group. Give you only maximum 30 seconds to upload. You don't have much time. Let's see your answer. Nobody have uploaded yet. Adwa. Okay, that's Adwa's answer. The rest of you? Ayah, okay. Why you draw sengit-sengit lah? Okay, Allah. Whose drawing is this? MH, who's MH? Who's MH? Mukminun.
Yes, Prof.
How come you don't even, brother, you need to study all the classes that you miss, brother Mukminun. You make sure you watch all my videos. Because your drawing, you don't even have the band gap writing of the energy band gap. Okay. Wow. Nasrin, quite interesting. Okay. All right. Everybody uploaded? Anybody not yet done yet? Anybody not done yet? Last one, Badul Amin. Now you see the right one. Okay. Now you know. So some of you, I don't blame you because you only learn up to there. Some of you are like not showing that you understand the previous one of my classes. Some of you show, but you are limited to what has been taught to you. Some of you are more innovative than you should be. Okay, so now if I were to draw this, if I ask you, I can ask, I think it's a good question. Maybe in the quiz, I say, I draw a structure, draw me in the energy band diagram. Or I draw you the energy band diagram, I ask you, draw me the structure. This when I say structure, it means the physical. Okay, this is physical, means you can see 3D. The physical you can see with your eyes. Okay, energy band diagram you cannot see with your eyes. So you should be able to translate between two. So in the final exam and some of the quizzes, when I ask you to design, when you design, you have to draw the structure. Many students doesn't draw the structure, they just draw the energy band diagram. Then you miss a lot of marks. And I'm warning, I don't know, I keep on warning the class, but still students do the same mistake. I'm warning you again. So I don't understand why student doesn't, take my advice. Yes? Cannot hear you?
Design tu
You are muted.
for the point titik-titik tu.
What?
Design.
Brother, you keep on off your mute. Your
sorry.
Sakit jiwa apa?
Design tu we must draw like a box or point. Something like.
No, when I say design a structure, the structure is like this. When I ask you to draw the energy band diagram, it should be like this.
Okay.
So it depends on what I ask you. If I ask you draw the lattice of it, you draw like this. Here.
Okay, madam. Thank you.
It depends what I ask you. So you need to read extremely careful about my question. My question normally paragraph. So everything you need to read carefully and then try to see what I want in the question. Okay, so the answer is the energy band diagram of that one. So see, okay, maybe I should draw it next to each other. So let's do this. I want to make it smaller. Okay, so I can draw next to it now. So we can see here we have three layers. So so it will be 1.6, 1 and 1.6. So I will start, you can start normally top and bottom, it doesn't matter. The top and bottom you can it doesn't matter left or right. So it means I can start with the top here and then end with the bottom, or bottom and with the top when you draw the energy band diagram. So here then I will start with, maybe I will start with the bottom. So 1.6 of this material, then it becomes 1 EV, then it becomes 1.6 again. When you draw the energy band gap, the gap, make sure you relatively you show how big it is, because I can see when Fatin drawing 1.6 and 1 is the same height. It shouldn't be 1.6 and 1. 1 is like nearly half, right, of the 1.6. And this is the energy band. No. And this 1.6 should be the same. So the height should be the same from this side to the other side. So I don't have a ruler here. So this is 1 EV. This is 1.6 EV. And then this is my conduction band and this is my valence band. Okay, that is the energy band diagram of this heterostructure. Okay. So it means that when it becomes heterostructure, it's combined. So I know you were drawing, you draw the, what do you call it, individually. When you draw individually, like your answers in the telegram, it means that it's not a structure yet. It's just one individual structure. But when it becomes like one structure, like heterostructure like this, so it must be like linked. Okay. All right. Any more question before I ask you question?
Hi.
Yes.
Just now you were saying that the difference in the lattice constant will affect the stress and strain, right? So like how big or how small should it be, the difference?
Huh? Again?
How small is the difference between the two material for the lattice constant difference?
It differs from material to material, so I cannot say.
Okay.
So therefore, if that's the case, maybe you need to do, if so you don't know, I also don't know. So if I give a material and you need to know, you need to search. Normally this kind of question, you need to search whether it's already beyond the limit, or you use your common sense. If it's like 3 times of the this is a rule of thumb. It's not normally not necessarily right all the time, but it's like 3 or 5 times of the lattice constant. Maybe it's already, you cannot even make a device out of it. There's not even defect. You cannot have a bond. When the lattice constant is too big, you don't have a you won't have a bond. You cannot make a structure. But if it's maybe close, like maybe like 1.5 times or 1.2 times, so that you can make a bond, but there will be defects. So whenever the lattice constant is not exactly the same, there will be defects. Okay, but how much, it depends on the relative difference. Any more question?
Madam, yang
Yes.
1 EV tu, kenapa from the middle, not from the bottom on the energy diagram at the hetero?
Who's asking?
Nizam.
It doesn't matter. From the bottom, macam mana? Here. Huh? Is it this?
Yes.
From
Yes,
the
yes.
bottom? What do you mean from bottom? No, it's not from bottom. It's from this. This is the conduction band. No, so this is the valence band for the material, and this is the conduction band of the material.
If I make it parallel with the other material, can?
Try to draw. You draw for me.
What I think what Anizam said is we need to start all from the same line from zero.
Same level.
I
Same
say draw
level.
it for me. Prove your what you want to say. Draw it for me. And then put it in the telegram. Good question. Any more? But I'm waiting for Anizam to finish drawing. Any more question? I will call. Yes.
Can recombination occur across the material? Means different materials, right? So can the recombination happen between the different materials?
Good question. You think? So looking at the energy band diagram like this, is it possible? You think? You know what recombination is, right? So this is a energy band diagram. Can you answer that question? Possible or not? If possible, how?
Maybe yes. I don't know for sure. Maybe the electron slip from another material to another material because it's free carrier.
How? You
can
tell
move.
me how? I don't understand. How?
For example, at the first energy band diagram, electron at the conduction band is a free carrier, so it move around. Somehow it went to the second energy band diagram, and then it can recombination through that.
Recombination is a noun.
Recombine through that material.
But are you answering his question?
Yes, he said can it, so I answer yes.
No, do you listen to careful? Brother, ask the question again.
How can the recombination happen across the material, and how it can happen?
What do you mean by across? Maybe Hazi understand differently. What do you understand? What do you mean by across?
I mean from the green materials to the red materials, right there, like that.
Sometimes, later you have assignment, so all of you have to ask questions. So many of the times, the student, even you need to answer your friend's question, and many of the times your friend's question itself is wrong. So that's why I'm trying to I would say why your question is wrong. Wrong because technically it doesn't fit with the definition of recombination. What is recombination, brother? From where to where?
From the covalent
Balik.
From the valence from the what?
Electron from conduction band.
From conduction band to
the
valence
valence
band.
band.
Okay, so that's a basic. You have to go from conduction to valence.
Yes.
So your question is, if I understood, technically, if I'm very detailed person, so I'm expecting you also very detailed, and your question, the way I will understand your question is very technical and detailed. So I will tell you how I understand your question. You asking me, is it possible? For example, so this is material kata A, B, C. So this is A, this is B, this is C. Okay, this material. So you're asking me from A to C to recombine through that, which means that you are telling me, is it possible for this, for my electron here to start here, because recombination is from conduction for electron, from conduction band to valence band, to go from here to here. That is your question, right? Who asked that question?
Nasrid, what I say from A to B.
Okay, so from here to here.
Yes.
Okay, here to here, possible or not possible? I mean, think about it. Okay, maybe you already think. The answer is the answer is the one that Haziq was asked. If the electron already comes here, right? Haziq's answer, the electron already drifted or drifted over here, move or drifted over here, and then recombine over here. It when this electron recombine over here, this is called recombination at B. It doesn't mean recombination from A to B. The A to B, the electron must come from here, go there, you know, from this energy level to this energy level.
So it's not possible lah.
I don't know. The answer is there's a kindergarten level or let's go PhD level. Mukminul, you need to know all. So the kindergarten level not possible. The PhD level possible, but it's complicated. So what happens is you can have like at the edge, it is possible, but it's very complicated and rarely happen. But if I say not possible, I'm lying because it's possible, but rarely and it's complicated. So for our level is kindergarten level, we accept it's like not possible. Okay. Any more question? Yes.
What is the kaitan, the relationship between lattice constant and the energy? Is
What energy?
Energy band energy.
What energy?
EV.
EV? Valence band?
Balance.
Macam tak logik je soalan awak tu. I don't understand.
Madam boleh tanya relationship between lattice dengan EV. EV tu energy ni, energy
EG
pandangan.
ke EV?
EG.
Tadi
EG
kata
kan?
EG. Yang mana satu?
EG mana EG.
Siap.
EG.
Jangan. Dalam semiconductor device, salah satu huruf pun awak inna lillahi wa inna ilaihi raji'un. I will give you 0. If you even one letter you got wrong, brothers and sisters, you will fail. I'm telling you. So think carefully. So it's good for all of you to ask a question. That's one level. Next level is let's think before you ask questions. Okay, make sure you don't make mistake between covalent and valent, you know. And apa nama ni, and also EG and EV, because there are two different things. Covalent bond and valence band is two different things. It's like we're talking about apple and pineapple. Two different things, right? So that's something. So try to be careful. Okay, try to be careful. So is there any relationship between lattice constant and the band gap energy? There is, but it's complicated. So therefore, it's a good question. Therefore, we have an interesting graph for that. So when we do characterization in the lab, when we scientists, engineers do measurement on our semiconductor material, we have come up with this what you call it, graph. So let's, alamak, kenapa dia tak nak? Okay, this graph. Graph of band gap versus lattice constant. And this graph is so important. It always comes in the final exam. No, I don't want to do this. Stop sharing. I want to share. Dah nak ambil masa dah. Tak habis lagi nak ajar macam mana ni. Okay. Alright, can you see my here? Okay, let's look at this. How do I make it big? Okay. See this graph here? This is to answer your question, Adwa. You have a relationship of a band gap and lattice constant for different semiconductor materials. For here we have silicon, germanium, gallium nitride. All of these are all semiconductor material. So how to read this graph? So if it's silicon, I know the band gap energy is 1.1 also, 1.1 EV. And then the lattice constant is roughly 5.41 Armstrong. So germanium, the band gap is roughly maybe 0.6 or 7, 0.6 or 7. And then the lattice
6.
constant is 5.62, something like that, Armstrong. So so you can see it's random. It doesn't mean that if you not random, it is how Allah created the device, no, the material. When this is all material from the earth. So in the periodic table, so everything have its own characteristic. So it have its own band gap energy and lattice constant. And this is very important. You can see here the what do you call it? So you can use this graph in order to answer some design question. The solid line show is direct band gap material. So when it's like dotted line is indirect band gap material. So if I ask you to make something with the blue light, you need to convert the blue light into a band gap energy, EV, right? Sometimes I give you wavelength, you need to I will not teach you how to convert energy to wavelength. That is A levels physics. Go and find out. You need to be able to convert between energy and wavelength. Okay, so that one I will not teach. I will assume you know. So sometimes I give wavelength, so you need to convert to energy. If you know the energy, for example, the energy coincide with 1.4, 1.41, you know, you can use gallium arsenide because gallium arsenide is direct band gap material. So, and this line that connects the line, so you can see there's line, and not only solid line shows direct. Another one, this line is connecting from one material to the other. What does this mean? This means that you can make heterostructure out of it. You can make heterostructure. So for example, silicon and gallium arsenide, there's no line linking them. So you cannot make heterostructure. It will not bond. Because as I said, it's complex. So this graph is just summarizing it. So without knowing much of the physics, if you're going to understand the physics, we need to do 3D integral. We'll never finish. We will become physicists. But we are not physicists, brothers and sisters. We need to learn physics here in order to design the device. But we are not physicists. If we are physicists, we'll be learning on what is the equation to get this. How do I know silicon is not linked to gallium arsenide? So for we engineers, we need to know minimal of the physics, but we need to know the physics. We don't know the physics, we cannot design. So that's why this kind of thing will help us. So we don't have to know the equation in order to know which one will connect to which for all the condition. You know, you need to integrate with condition, infinity or something like that. We won't go through the mathematics, but we just use the information available. So we engineers, we are like that. That's why physics doesn't like us. we shortcut. So for example here, I can say, gallium arsenide can be linked to indium arsenide. Although you can see the lattice constant is quite far compared to silicon, but because there's a solid line over here, I can make a heterostructure with gallium arsenide and indium arsenide, right? I can make with very minimal defects. Normally with the one with the solid line, if it's line linking to each other, we can ignore the defects there, although there's a lot of difference of lattice constant. Okay, so for example, you can, although this gallium, if I make a question in the exam, I want to make a heterostructure between gallium arsenide and silicon. So you should know that it couldn't happen, and I will ask you what will happen. So you need to explain what will happen. It means that if it cannot happen, it means there are a lot of defects, then you cannot get light and so on. So that's how you interpret this. Any question on this? This is very important graph. So madam, do we need to know all this semiconductor material? Yes. You don't have to memorize it because it's open book. but you need to know how to use the information.
Madam, why there is solid line and there is dotted line combined? For example, at the gallium phosphide and gallium arsenide.
Okay, that's a good question. Okay, okay, that's a good question. You know, it will take longer for me to answer this because when you have this, when you are linking two material together, for example, gallium phosphide and gallium arsenide, right? So you can make a heterostructure between gallium phosphide and gallium arsenide, number one, and number two, you can make a compound semiconductor. So it becomes gallium arsenide phosphide. Okay, so by playing with the percentage of phosphide, so gallium arsenide, there's no phosphorus. Gallium phosphide, there's no arsenic atom. But we can make a semiconductor material called gallium arsenide phosphide, GaAsP. So it means that we can vary the percentage of P, phosphorus. If phosphorus atom is 0, it becomes gallium arsenide. If it's 100% of phosphorus, there's no arsenic, it becomes gallium phosphide. So when you vary the percentage of the phosphide, it will be at one point, depending on the percentage of phosphide, at a point it becomes direct band gap. Furthermore, it can become a indirect band gap material. Okay, so that's why, as I told you before, we engineers, we like this because we can control to make it direct or indirect band gap by changing the percentage of phosphorus. So, for example, gallium arsenide and aluminum arsenide here, we can make another compound semiconductor. We call it aluminum gallium arsenide. So the band gap will be in between this, depending on the percentage of aluminium that we put. Okay, so because you asked this question, and but it's good. I don't know whether you can take it or no. Okay, more question? Any more? 451. Final question.
I have, but not about this diagram. But it's not about the diagram. It's about the energy band diagram just now. That the structure one. Remember how we were talking about when we have defects, we have energy trap level. So like how would it be like if it's
where will it be?
Yes, where will it be in the combined?
Question, it depends on the defects and what the defects are. So if the defects in the metal A, it will be in the band gap of the metal A. If the defects in metal B, it will be in the band gap of metal B. Okay. If it's in between, so in between, we need to do experiments. So we don't know. When we do know the experiment, then the experiment will tell us where the defects will be. Okay. All right. So looking at Anizam's drawing in the telegram, it's possible, but okay. When we have heterostructure, because you ask this, right? If you don't ask this, I can keep quiet and we can pretend that we all don't know and I don't have to ask you in the exam. But because you ask, so we have to know and we maybe come out from in the exam. So in heterostructure, we have type 1, type 2, type 3, type TYPE, type. I will just share the screen for a while, although we don't finish the time, because I want you to go and explore. That's why I say it looks easy. I'm trying to simplify as much as possible semiconductor material and device, but it's not very simple. But I'm trying to. Okay, we have type 1, type 2, and type 3 heterostructure. So, structure Venn diagram. You can Google this. So the one that I draw here, is one type. I can't remember type 1, type 2, type 3 because normally I don't teach in the class. The one that Anizam was drawing is one type. So how do we know which type? We don't know until we do experiment. So that's why we will search for it. We have a lot. That's why we scientists, engineers, we read a lot of journal papers. You do final year project, you also read a lot of journal papers. It's your job for you, especially if you do masters or PhD, to read journal papers and to understand, because that is where we get our information. So in the journal papers or the internet, you can search and they will tell you if you have this kind of if gallium arsenide plus indium gallium arsenide, which type is it? Type 1 or type 2, type 3. So then and this is called the band alignment. Nama dia, they call it the band alignment. How the band align. So depending on what material and what material, it can be type 1, type 2 or type 3. But the most common one which I'm teaching you is this type. You'll be somewhere in the middle. Okay? But if you want to answer type like how Anizam is drawing in the final exam or quiz, you can, but I will check whether it's right or wrong. So if you want to be safe, just use this, the most common one here, the one that I'm drawing. Okay, so that's the answer. So for next class, I want you to, nobody asked me this question. I want to ask you why, nobody asked me why do we need to have heterostructures? Why make it complicated? Why not all homo structure? Okay, find the answer of the question and answer me in the next class. And it's actually very important question and very important answer, because otherwise no point we're learning about this. We don't know why is it important. Okay, I think that's all for today. Wow, there's like mosquito in my bed.
Attendance, madam.
Oh, attendance. The password for today is heterostructure. So that you remember what is homostructure, heterostructure. You will use this heterostructure for laser, LED later on. It's very important. It's extremely important. I think most of nowadays, most of any semiconductor device is actually heterostructure. No, nothing is homostructure. Then you go and find out why. Okay, I think that's all. All right, can we close the class with the dua, please? Volunteer from one of the brothers who have not recited the dua. You know who you are. Otherwise, you will stay here.
Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Allahumma ighfir lana dhunubana wa liwalidayna warhamhuma kama rabbayana saghira. Rabbana atina fid dunya hasanah fil akhirati hasanah wa qina azabannar. Sallallahu ala sayyidina Muhammad wa ala alihi wa sahbihi wasallam. Alhamdulillahirabbil alamin.
Alhamdulillahirabbil alamin. Okay, thank you, brother. So inshallah, see you next week. Let's end with tasbih kifara and surah al-asr. Subhanakallahumma bihamdika nashhadu an la ilaha illa anta nastaghfiruka wa natubu ilaik. Bismillahirrahmanirrahim. Wal 'asr. Innal insana lafi khusr illa alladhina amanu wa 'amilus solihat wa tawassaw bil haqq wa tawassaw bis sabr. Please study for your quiz. I will try to make it as hard as possible. Why? Because just to make you realize, if you play, then you will fail. So don't play around. Okay, Assalamualaikum warahmatullahi wabarakatuh.
Thank you, madam.
Welcome.